We're going to enter physics monk mode, okay? Which means if feel invited to join me. But the first thing for me it means is I want to be able to think better, because sometimes I think worse, sometimes I think better. Right now I want to be thinking better, so I need to have better posture. I need to have better blood flow. I need to be in less pain. So if there's anything, even if it's small, I can do right now to make my neck hurt less, my backbone, oh, that helps. Okay, right? This is I'm not saying everybody has to do it the same way, but if you can identify something to right now, just shift and make it so you're more comfortable, in less pain, but maybe also more awake. Okay, like so be more sitting up instead of relaxing on the couch. Also, it really helps to on purpose try to breathe a little deeper, because the most important aspect is your brain's getting enough oxygen to have the energy. That's just physically the most simple thing you can do to wake your brain up more. Breathe more. I'm asking you guys to kind of do it with me a little bit. Now, we're going to start from the philosophy, or maybe the ultimate aim of why the project we're all excited about is so exciting. And I'll try to throw, in some of these conversations, I have to use words like consciousness and stuff, so I'm going to give a definition, which is always appropriate because there's widely different ones used, even in different fields, right? So for me, I see there's an intrinsic goal laid out into consciousness to gain more consciousness. It seems clear to me that consciousness is always excited and thrilled when it comes to an understanding of something that collapses the thing it used to think about the world and it repopulates it to a better explaining world. A world where more things make more sense, right? This is the whole process of growing up. It happens over and over and over. The clear definition for consciousness would be something that tells story, that situates it in an environment. So it has to tell a story about what the I am and what the they is, or what the out there is. So it has to make a story of the universe. And it doesn't have to be a correct one to have some level of consciousness. The story is the first step. So at the level of complexity where something can model an exterior environment and tell a story about what it means, see, okay, then there's some form of consciousness happening. You could be seeing wrong, completely wrong, right? Because your brain just decides to tell you that that's the answer every time. That's what you see. Because you have to be able to, you can't see until you have a way to translate the input, okay? So the whole process of sight, the way we currently see the world right now, won't be the way people see the world in the future, just like it wasn't the way people saw the world in the past. Really, really, really important. But we also grow up in individual experience through life, through several of these stages of seeing the world a certain way and then seeing it another way, and learning how to investigate the world with new tools, and then discovering a whole bunch of new things and seeing the world a new way as a consequence, and so on, right? To me, the ultimate goal for anything that is at any of the stages of consciousness, anything that occupies a story about what the world is and what I am, and everything that in between, therefore creates senses of meaning and so on. It defines your experience and your existence, but also the limitations of how you can try to intentionally manipulate your environment and extract what you need from it, right? If you don't know there's an underground river just 10 feet down and you starve, you die in the desert because you had no water, the information is what really killed you, not knowing what your environment was really providing. Okay, the more you understand your environment, the more you can take advantage of what's there, which is our whole history of humanity. That's our whole technological rise, our whole rise in science, changing the perspective. Technology changes, change the perspective, and technology changes. And they're advancements because the new technology covers being able to do what the old technology could do and more. The goal is to then be able to occupy a conceptual frame about what the world is, to be in it yourself that's correct. Correct in the sense it doesn't limit you in any way other than what physics limits you by with interfacing with the real world. Okay? It makes it so that you can engage with everything electrons can do, everything protons can do, everything neutrons can do, and all on the way up. We can measure that these atomic properties keep coming up. There's these atomic restrictions, there's atomic reactions. So the atoms are a part of the world for sure. But what the atoms are is not such a clear picture. Why those interactions happen from those sorts of things is not such a clear picture. There's a lot of magic still in the story. The goal is to go from that which isn't the most informed story we've had so far. I'm not putting it down in any way. It's the best we've had. We want to, it's clear in the story that there are whole things we don't know how to answer. So we want to get to a story that doesn't have those restrictions, a story that empowers us to understand how energy actually quantizes itself through all the actual chemical interactions that are available to atoms, right? We want to understand what atoms truly are. What kind of boundaries do they have? All of them. What sort of boundaries? Is it one simple boundary? There are lots of different kinds of boundaries. Why do those boundaries enable them to do every single exchange that atoms can do? Let's say there's some ultimate limit, the theory of everything, a mindset you can occupy that connects you simply and directly to the actual physics and chemistry and so on in composite forms of the exchanges going on in reality. It makes you actually understand them, see them, okay? That mindset is the only one completely free, bound by the same actions that bind physics. You see what I mean? There's a concept of a limiting perception up here, right? That's the perception you would imagine a God would have, right? A God that was able to create a universe or understand its entirety would have the picture that connected it all together. There's this concept of a mindset in which you already see the world through that lens, through the physics lens, the connections in atoms and so on, so well that you could learn to think the way you think you're thinking in English or whatever your tongue language is. You can think in operations, right? In building construction sentences and sequences of things that transform something into something else. You learn to think in biologic transactions or chemical transitions. That would be a beautiful improvement for me. But that means you would also then be able to think your way through how to make stuff. Right? And maybe not everybody has to be able to spend their time thinking through how to make stuff. If you had a system that put together the construction of how to do all these transforms, if you could see how the system fit together, if anyone could, and you put it in a computer, is now programmed. It's going to be the same system tomorrow. So if humanity gets anyone to the point where they understand the constructive connectiveness of the actual structure or shape of the universe that allows the physics of the universe to exist, then they've now transcended all the local barriers we've grown up to this point in history. All of them, all the barriers are gone. Money doesn't matter. You can make replicators. You can use a computer to make any physical object you want. You can start making new ones. The understanding we would occupy in that level would not have anything to do with resource control. You know what I mean? From others. Your position in life, your experience in life wouldn't be oriented around the need to be able to get resources. That's been overwhelmingly available now. You've got any resource you want. What are you going to do with it? It's completely different engagement. And I think consciousness has been growing for that purpose the entire time. All the stages of changing, it's been trying to gain more access to its environment so it can experience in more enriched ways. It's really just occupying a different mindset. Seeing differently is the same thing, by the way. That's how you know. How am I there? Well, you see stuff differently. Literally, the world looks physically different. I'm not making an analogy. It's gone all through your life like this. You didn't see like you see now when you were 3 years old, right? It's the same sort of thing. You'll be able to see differently. You'll be able to see stuff that's just a mystery word right now, like a black hole. It will become something you can see. Right now, the way you see forbids that to happen. But when you transcend to the other way of seeing, this conscious story of what reality is and how it's constructed and how its transforms can occur, then the evolution paths in this geometry, in this structure, becomes something that you can comprehend, you can grasp, you can hold, you can dream about. They're not mysteries. We're not there right now, and I think that's exciting. Because as far as I can tell, that's the highest aim consciousness has in it. So we're not living in a world that's reached it. Not a single individual ever has. We're pre that. But we may be living in the time where it happens. That's the biggest event in history to me. That's bigger than the moon landing. That's bigger than the first time aliens visit, if it ever actually happens. Okay, that's the biggest event in history. The event in which consciousness gets to climb itself into a position where it can see the real world. By seeing the real world, by knowing that there's firewood right there, you automatically have the ability to go pick it up and do stuff with it. If you can't see it's there, you never will. Right? To be able to see the real world, the one that makes sense of physics and chemistry and so on, right? The one that automatically does it in its own right. Its own structure is accountable, not another feature thrown on top to tweak it. It's just the thing that does that. Then we'll be living in a world where we can see things we can't see right now. Richly, our consciousness will be more empowered than it is right now. We'll be all richer than the richest person in the world right now. All. We can do more than they can do. Right? And because we understand something differently. We still have the same biology, the same genes that gave rise to us, but we changed our perspective the same way we have thousands of times growing up. But if we get the one that actually nails physics, consciousness reaches its full power. In my thinking, that's the point where we actually get someone who reaches full consciousness. Right? Everyone else has been shadowed, trying to reach to more and more consciousness, but the first state available for full consciousness is the one that affords you to see reality as it is. So, to me, it's the most exciting thing available, and a thing that's available to the highest sense of us, our consciousness. Okay, and the story in science is the systematic attempt to try to get there, right? Using measurement, using all the serious tools we can of logic and thought and physical tools we can design to measure things, to see what the world's actually made out of, over and over and over. When we do this, what happens? When we do this, what happens? Okay? Measuring these things and documenting these things is what science is about, so that we can come to a richer understanding, a different story than we currently have, one that accounts for these new things we haven't even tested yet. So let's go test and see what the world is, and then we can try to tell the story about why it's like that. Okay, this is the process of science. Now, it's not guaranteed that just because you measure a new effect in the world that no one's paid attention to or measured before, and then we can now all measure it and find it because we know to look for it, it's not guaranteed that that's going to immediately make it clear what the new model is. Right? Discovering a new mystery, a new element of the world, doesn't kick you out of your model. It kicks you out of having a coherent model, even though you're still on the same model. Your model's no longer coherent. There's something in the world it can't explain, right? You weren't aware of it before, so you thought it was a coherent model. But now you know it's not a coherent model. So you have to be in search for a new coherent model. But it can be really difficult. It might lead to discovering 50 new things in the universe or in the world as properties that exist, things you can attach numbers and dimensions or dimensionless ones to, that other people can also then go measure and come to the same number. You can come up with 50 of those things and still not have a new picture for what accounts for all of this. Each one's a clue of some sort, but it's only a clue if you know what model to fit it to. Okay, so it's a clue trying to hint at what's wrong with your current model, and that's as good as you get. You get a clue. It doesn't tell you what the answer is. The answer is only satisfying or believable if it fits all the pieces together, all the things that you've got to account for. CODATA has got the whole list of the constants in nature, the physical aspects that we want to explain, or that we need our logic to account for, if it's going to be actually matching to the symmetry transforms or actions in chemistry and physics that we see. I think it's the most exciting thing that any thinker can occupy, is a better world sight, right? The one that sees the world more richly, with more of what is actually in it. I'm not talking about becoming more, this is interesting. I'm not talking about just inventing more things to imagine around you. I'm talking about your imagination discovers that there's another thing in the world to pay attention to. And when I pay attention to that detail, there's that, now there's this, now there's a lot new stuff in the world that somehow depended on that detail. Okay? That's probably more familiar to everybody. I always wonder if what we say is being an adult means that you stopped changing that way. It seems like that seems to be at least more common to be true, maybe not as a rule, but I think the pushback in philosophy is to try to get every child or everyone to recognize themselves as a child compared to the mindset that actually makes sense of things. And then be excited about the gift or the ability to chase it. Okay, I took all the CODATA constants in nature, and the first thing I wanted to do was figure out how can I, this was after trying to make sense of the whole world and writing Einstein's intuition and stuff. This was many years invested in physics and reading other physics books and the old masters in physics and trying to keep notes on all the things that didn't make sense to me yet. Or it seems that this person explains it clearly this way, but this person explains it clearly a different way, and they're different models. I don't know which one now, I'm confused, so I keep track. I was really trying to make sense of the world. But then the model I was building ran into a solid dead end that I couldn't transcend. So my next step was to say, okay, how about we just take all the data points that you would need to explain, all the features of the world you would need to explain, if you were to come to me and say, hey, I've got a theory of everything that explains everything. Okay, I'm willing to believe you if you show me. What exactly would you have to show me? You'd have to show me that your story, this short thing that you wrote down, a logic form, a geometry, or some sort of story, that story would then have to be generatively in a simple way that I could easily explain all the actual features we needed to explain. That's it. There's many ways to do those sorts of things, right? But that's what it has to do. Your story has to actually come at some point and explain the speed of light. It has to explain the gravitational constant, not just give me a universe that has a speed for light. It has to explain the speed of light. That's a huge restriction, right? Now we're using the measurement tools we've invented so far, all of them, the best of our measurement tools, all the way out CODATA and CERN, okay? Our best measurement tools so far to read into the structure of reality and get a measurement. And as we all are familiar with, the best measurements approach 14 significant digits. We don't have exactly full 14 significant digits for any measurement of any kind, of any feature, or any expression in the universe. Okay? 14 seems to be a cutoff, or at least at this point in history. I'm in the camp now where I think it seems to be a fundamental cutoff. What I needed to do was take those features, CODATA's list of features, and find backwards a story that could account for them. Mine, the one I worked for all those years, my best guess, my best modification on someone else's best guess, and so on, failed. And I knew why it failed, which was the nice thing that I could keep going really well. I knew it failed because my story gave a geometry to gravity that made it feel good, except for the base cell, the base unit of my geometry, made no sense. It didn't make sense for why it was there by itself. Like, how did it get to be itself? Like, where did it come from? So I could come up with a handmade idea of a structure repeated and then the interactions implied and so on that would give us the same sort of effect, but I couldn't explain how it could even keep itself for an instant. Okay? The bubble itself of quantum space theory, if you know what I'm talking about. So in this case, now we're going to go backwards. We're going to say, let's take all the features we would have to explain. Let's look for what they have in common. Let's look for a story that tells that commonality. And let's see if we can keep going until we can tell a story that gets a hold of all of them. That was the kind of goal. Because that's the only story that would convince me. The only story. You might be able to come up with some cockeyed, pieces of things put together that tweaked on purpose came to exactly the speed of light. But it had a whole bunch of weird parts that just don't make sense why they're in there. But if you had a simple, short story for why the speed of light is why it is, immediately I'm on board. If that same sort of story extends to the gravitational constant, now you got me hooked. Okay? And if you can get the Planck's constant and keep on going down to get all 288, I really love your story. Your story is talking about a system that can give these things, and now I can ask, what are these things? It means something, and the story is going to have the same kind of flavor as an answer for almost all of it. The things that they have in common list, let's make sure that everyone can see them at least. All of them are going to have some symbol, and that's just historic in most cases. Sometimes it's clear why it's a symbol when you hear the name and so on, but for like the speed of light to the 8 meters per second. Okay, so that's one of our 288 features of reality, the things that are responsible for the stuff atoms can do. Okay, that's just one of them. It has a symbol, and then it has a string of digits, power, base 10 power, and in most cases some dimensions. There are some dimensionless ones. Okay, in this case we have two dimensions. It's the relationship between the meter and the second. And by the way, in the constants of nature, there's only certain kinds of dimensions to count. Okay, lots of copies of the same sets of dimensions, but it's just 5 base dimensions, bases. We got the second, which is the base of time. We got the meter, the base of length. We got the coulomb, the base of charge, electric charge. And then we have the Kelvin, base of temperature, and we have the kilogram, base of mass. Now, it's common to have taken enough math to have been told bases are random. It's not common to have gone far enough to realize, oh, yeah, they all started out as random, and then we invented a system based on the constants of nature to get the ones that matter in science. Okay, and these bases now are defined as the SI system. They have had older definitions. The ones we use now for the definitions of these 5 make the SI bases that are extracted completely from the constants of nature. Okay, so they are a conversation about how these weird 288 facts of reality that we haven't yet to explain by any model of reality come about. Okay, so somehow these are the ones of the system. There's 5 kinds of one in this system. That's one, maybe another way to see this. Okay, if you like the number part. I like numbers now. I'm starting to like them more and more because they contain secrets I didn't know to look for before. It gets exciting when you discover a few more new ways to get these secrets out of the numbers, which is really fun. But here we've got kinds of information. We have a string of digits. We have a power of 10 to the 8. We have meters per second, 2 dimensions. Why do we stop at 8?
That's our precision.
Yeah, kind of. We probably measured something close to 8, 8, 2, 1, and with a parentheses error bar. Okay, there was an actual measurement originally that the speed of light was coming from. This number, since I cut it off and didn't put ... or didn't show you the error bars listed, that's more important, means that CODATA is using this number so that it can define the 1 for the meter and the 1 for the second. It has to pick a set of the constants of nature to trust and then say, okay, now we can define the base, the 1. If you can't connect your system together, you can't even get the 1 defined. So that's what this is about. So these bases are literally part of the conversation about what reality is constructed by. Okay, that seems awesome. The second, familiar to us, tick, 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 right? The second is a base of exchange of a certain kind in the constructive features of the world. Really beautiful. These are the unique ones, the unique types of one in your decomposition structure or in your arrangement or just in your logic itself. I mean the inclusive or in all those cases. We have 2 kinds of constants of nature listed at CODATA now. So it's going to go a little more complex. Let's do that. This first one I listed is one of the ones they picked as the special set to define the bases off of. Okay, they've changed that set with updates. Okay, less and less so though. The other constants will come with string of digits. Like that. Something like that. I'm making this up entirely. Okay, but the structure of the features in our constant is what I'm trying to point to. So we have ones that are going to be cut off, defined now as 0, 0, 0, 0, 0, 0, 0 from then on. Okay, because we chose them to have our ones be clear, at least out to that resolution. And then we'll have other ones that are listed with the actual measurement error. Precisely valuable information, that measurement error. Tells you exactly how much to trust the listed number. And what scoping do you need to land it, okay, in order to think the number really lands there. That's a lot of restriction. Each digit helps you with another 10-fold restriction, right? This one's exact. This one's measured. But we're going to, in both cases, have a base 10 power between sum of our bases. This is a symbol for kilogram, that's a meter. Okay, and then the entire list of our mystery features of the world, this is how measurement has allowed us to access the relationships. Those are the clues. This is what we know about reality on the highest abstraction, about its deepest form. This direct measurement of what it is. Our highest current abstraction of it are these string of digits, base 10 power relationship between bases in our logic system. That's it. So that's the system's parts. Now we have to come up with some geometry, some logic, some story that makes those parts make sense. I don't get to change that the speed of light has this value, with it meters and seconds for the bases that express it. But none of that's up to any of us, but what we do get to try to do is find the story that embeds those features. But if you use it the other way around, if you look at these features and then try to find the story that unites them, we can actually chase it. So that was my process. And it took a long time. We chased it. Matt's been helping me for years on this. We've used Wolfram Alpha to put in the constants of nature, to compare the constants of nature, to look at all the possible relationships we can think of systematically. So you think of a new relationship? All right, everybody, let's ask that question to you. Okay, so it could take you a month to get through just that one question you came up with today if you're going to ask it against all the 288 features and their combinatorics. Okay, so we've been at it for a long time, and we've found two amazing things that sped up our goal of trying to get to a story. Okay, remember, our story is not really fully satisfying until it counts for all the features. But one of the features that shows up a lot and famously in physics is the fine structure constant. Alpha is its symbol. The fine structure constant is a dimensionless number. So there are many people not caught up with these being the bases that the exchanges of logic and physics are going on. So they're not directly interested in, say, the speed of light because it has these bases in it and they think those bases are random. But those people are still interested in this fine structure constant because it doesn't have any units. It's like pi. It's dimensionless. It's telling something geometric, but when it comes to pi, we have a lot of stories that we can tell you geometrically what it might be saying. Right? There's several of them that give you exactly pi. But this number, the fine structure constant, nobody had any idea. No idea. So the search was on, the quest was on to try to come up with any story. Okay, and we judge stories like any story would be judged. Okay, if you come up with a story that's made out of 1 million parts and it gives me this number, go away. I don't even want to memorize the million parts. You need to give me a short, an elegant story. And if someone else comes up with a story that is made of half the number of parts of your story, I switched the first instant I heard it. That's how it works, right? That makes more sense. And look, it gets us there. So that's what we're after right here. We're looking for, it's basically a contest and come up with all the stories you possibly can, but the shortest, most beautiful ones would be most likely to be believed or looked into more deeply. Okay. Well, the thing is, there weren't really any impressive candidates. Why this constant was like the one that got us the most. First of all, you have to get the digits right of the fine structure constant, at least out to the measured precision at the point in time in history. Okay, why this constant got us 5 significant digits, and it's a hodgepodge of factorial stuff and numbers together. They don't look like they belong too much, and it's hard if you stare at it for like an hour. You're still not going to make much progress in what this might be talking about. It just looks like it was just made up. Honestly, if you try to give it a good go, it still looks like it was made up. So it's not super exciting. Okay, and it only gets you 5 digits. At the time we had, I don't know, 8 or 9. So it was clearly not even also the answer. Okay, so I've been searching for this. I wrote a book that made it clear what my search specifically was. Somebody read that and contacted me online and pointed me to a blog where somebody had noticed something rather remarkable. A simple geometric expression they could write down that then gave them an approximation for the fine structure constant that got to 8 digits, not 5. It was 1,000 times more accurate, getting real close to the actual number we had, like 11 at the time. Okay, and it was only made out of pi and e.
Can you show us that one?
Yeah. 1 over x plus x cubed. Well, this isn't how he wrote it, but it's close enough. I read it, and let me modify the way I say it then. Let me say pi and I now. But he could say pi and e. He gave me the same form here. He gave it to me in this. I could change it to this from his form. It's squared. But then I just need to take the Planck mass normalized by the kilogram.
I to the I.
Yeah. So this is what we call the hyperbolic partition equation. It's just a logic. You can write down a polynomial. Its highest power is cubic. It's divided by 2 pi, not the most mysterious number anymore. It's a beautiful one we're all familiar with. And here we've got 3 different x components. Let's look at them piece by piece. Y equals, let's take the first one, 1 over x. Anything interesting in that logic? Anybody know? What?
It's an inverse.
Okay, it's an inverse, but also
Yeah, why?
not a line. It's looks like okay, that one's going to bed.
Oh, I see what this is doing.
1 over x is that graph.
Oh, that was logarithmic.
Yeah, and it's 1, 1, and now this area is 1. It's 1 by 1, right? And in order to get to the next 1 area from there, you have to go out to e. And then the next one's e squared, and the next one's e cubed, and the next one's e to the 4th. You just powers of e to get to units of area of 1. Okay, a really beautiful connection in this simple graph. And in fact, this is the simplest graph that's just not the straight line, right? Okay, then we have y equals x. That's the one I just mentioned, the one that is just okay, why is that an interesting graph to have in a system? You know why?
It's mirrored.
Yeah, it puts a mirror symmetry in the system, right? I mean, it goes down this way too. It divides everything in half at the 45 plane. Okay, and then we have this x cubed over 2 pi. A little more complicated, but there's a cubic term. A cubic is like a volume term.
Yeah.
Okay, so go ahead.
I'll do it, you do it. Sorry.
Let's make this here. So this is our, I should make it foreshadowed so it's easier to pay attention to. We only have 2 rules for the logic of our system. This hyperbolic partition equation and the coherence link of our system, the bipart system, which we call the
Binomial constructor.
binomial constructor. Yeah. By the way, this equation here, since it's our conductivity equation of the system, is saying that everything is hyperbolic, first of all. It's hyperbolically bound, so it's going to obey all the rules of hyperbolic geometry. It embeds naturally the rules of calculus that way. Really beautiful. But it also tells us that there's a scale significant to its construction. It's got a scale parameter right here. It's normalized, so it's dimensionless, but it's got the 2 limits of mass in physics, the Planck mass and the kilogram. The kilogram is the base, the 1. The Planck mass is the boundary. It's the 0 or as close as you can get. It's the thing that bounds that. Okay? All right, and then we have this weird, some people are eared out, but you can change this into an e to the negative pi over 2 also in there. And stack those up, you can see that geometrically easier. But this is just talking about unitary rotations, right? We got an I with a length, or 1 with a length 1, and it rotates up to 90 degrees from there. And that's where we get I. And then we have another one that independently rotates, but in the same plane, constructing our feature, and then raised to this power by that much. All right. This, by the way, is another way of writing the same sort of kernel that you can get for the analytic continuation function. Really beautiful. Okay, so Our hyperbolic partition equation, think of it as our connection equation for how the parts fit together in the structure. All of them, it's scale dependent, but it gives you the entire span of scales for the connectivity in the system. Okay? Now, you don't have to think it's the correct system it's expressing yet. I'm just pointing out this is an equation that expresses a system and how all of its scales are expanded. Okay. The other equation I already have down here is very simple. It's made out of two parts. It's got one part that has a geometry and boundaries, and another part that has geometry and boundaries. And those two parts act on each other for each exchange called the constant of nature. Okay? That's the story we've come to, and it radically reveals pattern and order in that entire story. Radically. It's beautiful, really beautiful to stare at, but also to then chase further for the full story that's what's going on in our connectivity. Okay, so these two parts just have boundaries and actions. And in this boundaries case, instead of making it a B there, it's a fixed set of boundaries. So the whole system can have different kinds of geometries acting on different kinds of boundaries, and then the reflection, or the other half of the system, is going to have a certain set of boundaries, or sorry, a certain set of geometric actions on the inversion boundaries of the system, the internal boundaries. And everything that inverts has to invert, including an action on those. So this is the inversion of the internal boundaries, or the action that inverts them. And this is the action that inverts the external expression, or the boundaries on the outside of the domain. Okay, so we're splitting the domain into two pieces, that's it. And both of those pieces are made up of two pieces of the same kinds, actions and boundaries. So it's not incredibly complicated, but it has two forks there. Our quest to try to find a pattern took years at that point, so I'm going to speed up through all the hard work so we can get to the story we eventually found. Because that's what the one we're trying to get exact and precise and as beautiful as possible, but also as informative as possible in our own heads. Okay, so through that whole quest, and by the way, we didn't start out knowing this one or that one. We got this one from this quest, and if you plug this equation into the computer, it solves for x. It finds the roots of this form. Structure here has 4 roots. And the first root squared is the fine structure constant. Okay, so this is the reason we're interested in this structure, is this fine structure constant is littered all over in the relationships between the constants in nature. Take this one, divide by that one, alpha. This one divided by that one, oh, it's a square root of alpha. This one divided by that one, oh, it's the square root of alpha divided by 2. This one, oh, it's alpha squared. It's all over the place, okay? So it's connecting things in chemistry anywhere that the electron interacts. Okay, it's huge. So we want to have a story. Here's a story, finally. Let's see where it can take us. Well, the first thing it takes us to is a structure that's connected hyperbolically. So it's got a whole integrated system, there's a rule for how things integrate. But also, it's 4 roots. Okay, first root, we give it the name that, Je1. So the second root, I'm going to give a symbol for, call it Je2, Je3, Je4. Now, the reason we came here is because Je1 squared equals alpha. Wow, okay, we have a system whose has a number that lands the thing we're interested in. Let's see what else, the other features we can connect to that same system. Because if we can connect all of them to this one system, then we have a story. We have one story connecting all the things. So this is the hope at this point, right? These other roots have to play important roles. Otherwise, this is just kind of a cockamamie story. It happens. It's kind of a coincidence. It has one fit. It does one thing. It's like really cool. We finally found a story that does one thing, but if it can't do anything else, not so exciting. Let's hold on to the hope that because we have something that can land the same number we really care about, which puts together the actions of chemistry and so on. Let's give a little hope to these guys that they do something in that story too. Okay, let's try to figure out what that story might be. So let's see what they do first together. All right, let's take these guys. What's a way to take them together? Product. Okay, so the product. The sum. Yeah, the ratios. Squared is another one. This is the classic way to go with squared. Let me stop talking. When we're checking beta relations, which means relationships between the roots of the polynomial. Okay, that's what we're doing right now. We're looking at relationships between the roots of the polynomial. Yeah.
What about a sum of their inverses?
Good, exactly. We can do the opposite, turn everything upside down, do the exact same thing. Okay, great. There's lots of relationships. We can talk about all of them about at the same time in these ways, right? Okay, and these are classic ones to check. So here we go. This one, these are strings of digits. Strings of digits, both one-dimensional number, and then J3 and J4 are two-dimensional, one with an I, okay? Strings of digits. They don't look recognizable in any way at all, but now in combination, we get 2 pi for their product. In this different kind of combination, we get 0 for their sum. In this one, for the quadrants, we get negative 4 pi. Now, I'm never going to go back from wondering whether or not they play important roles. Their relationships are all important. If we got a system, something to do with 4 pi, something to do with a 2 pi, and a 0, those are all numbers I want in my system. It's going to be recursive and balanced, persistent, and so on. Okay, that's nice. All right, the other ones to check is to take their byproduct sum of the roots. Does it make sense what that word means? Byproduct. 2 of them multiplied together, and then take all the ones that you can multiply like that into pairs, and then add the pairs.
And all those combinations?
All the combinations of pairs and add it together.
How many are those? Never mind.
Let's do it. We got 1, 2, 3, 4. What's our byproduct sum going to look like? 1 times 2 plus 1 times 3 plus 1 times 4 plus 2 times 3 plus 2 times 4 plus 3, 4, right?
Yep.
And this also equals 2 pi. Really beautiful. And what I'm saying, I'm not telling you to 14 significant digits. I'm telling you to all of them. Okay? J1 is one-dimensional. If we add it to the other one-dimensional one, is J2, and compare their sum to the sum of the two-dimensional ones, beautiful. Now, I know if you've got a little bit of practice in combinatorics, we like to do sums and products of things, and when there's interesting sums and products relationships, then things can become very symmetric, and you can do lots of things with them. Well, -1 is one of the most beautiful things to get, because you've now just inverted, and the process will start over. So algebraically, these things are telling us lots of interesting clues. The thing is, since this algebra came from this form right here, we can rewrite this form to look like a more familiar polynomial. Traditional polynomials don't have an inverted power. Okay, so all we have to do is multiply everything by x. So this one goes away. This comes x squared. This comes x to the 4th. Okay, but then we also have to multiply everything over here by x. And we do that, and we rework things and write it as a mono, as a.
Does the answer always have to do with unit pi?
No. Good question. Okay, I skipped that, so let's unskip it. First A, okay, that would be this one. The triple product sum. Just like this, but now we're going to go up to triple products. What are those going to be? 1, 2, and 3 probably first. 1, 2, and 3. Now this is what we would do if we had any system with 4 roots. We would ask all of these sets of questions so far. I mean, more, I'm skipping some, but these are the traditional central ones, okay? Now we're going to add it to 1, 2, 4 plus 1, 3, 4 plus, we're out of the ones now, so 2, 3, 4. Okay, so that triple product sum equals 2 pi times A, and A is equal to 1 over J1 plus 1 over J2 plus 1 over J3 plus 1 over J4. These determine our spectrum, so this is our spectral parameter of the whole connected system. And this is how you would talk about it for any polynomial that you've fit together. Find its roots, Inversion of root sum gives you the spectral parameter of the system. Okay. All right, so this value A, and every other combination algebraically of the roots themselves that have a power or a multiple of A in it, now no longer direct things with 2 pi and everything. They now have this in there too, but yeah, the rest do. It's a big set. Okay, so algebraically we have a lot to be interested in here, and this is the traditional route to turn something into a polynomial to then convert it into a matrix, right? They're the same thing. So let's look at the matrix form of this guy. So far, this fine structure constant is now being nailed to a story with a lot of rich and interesting complexity that we can pin out, not just one match between this and that so far, okay? But the goal is going to be able to try to then tie that somehow to all the constants of nature, the system that we're trying to understand that transforms and stuff and connects via this thing and so on. Okay, what was I doing right now?
Matrix.
Matrix. Oh, the matrix, our companion matrix that goes along with the polynomial of this form is, this is really, really simple computer logic for the connection between the system. First thing, it's a 4x4 system. So going lower than that, you're missing part of the construction of the boundaries of the system. So there's no lower than that if you want the full explanation. But this is also the full explanation of the connectivity. Think of it as a register exchange. You're moving forward this way and this one and this one and this one and this next one. By how much? Tells you in each case. Right? Things are getting back to the start, and then now we do the same thing again over and over. So this tells you how your system just evolves over time. The step forward operation here by 1 as we go down, and then those multipliers to bring us back to the starting exchange position. Okay, now we can operate or look into this through the classical systems of matrices. When we're looking into the matrices, we have a bunch of properties of matrices. First of all, they have eigenvalues, the most important things we want to start with, right? The eigenvalues of this matrix are G1, G2, G3, and G4. It's going to play the exact parallel story role. So I mean it literally when I say matrices, and polynomials encode the same information. So we can tell the same story now in terms of matrices for every property we talked about. Okay, that's the story we're at for the connectivity of the structure that holds our system together. And this is the story we're at for the 2-part exchange of the transformations allowed in it. Okay, boundaries and actions on the boundaries. Okay, so using that story, we then now take the data points, 288 constants of nature listed as strings of digits, powers of 10, and relationships between bases, and we tear apart the information according to this rule and this rule. The according to occurs in different ways. In this case, the according to means the string of digits have to be equal out to the first 7-ish digits, to the left hand of the story. We can ignore the right hand because the box symbol has a value, a dimensionless value of real close to 1 times 10 to the negative 7. So that means that the value, the contribution to this system that this guy over here plays is shifted by 1 times 10 to the negative 7, whatever the A is. So it doesn't come into the story until about here. Okay? So now that's what we're going to do. We're going to take every constant of nature, including the speed of light, and pull it apart in terms of this and this piece. Look for the boundaries that account for it and what action is on those boundaries, and then look for the other part of this story here. Let's do it real quick for the speed of light. The speed of light equals some action on some boundaries. The boundaries aren't something we're just going to guess. We're trying to tell the story in terms of the limits, the boundaries of these coherent 5 bases. So we're going to do it in terms of the Planck constants. So here, the dimensions are meters and seconds. We want the Planck constant boundary of meters, which is the Planck length, divided by the Planck constant boundary of seconds, which is the Planck time. That's our boundary expression. It has the right dimensions now, meters per second, okay? So now we want to see what number do we need to have in front of it, this A, in order for it to match the first 7-ish digits here. It turns out you need 1. Well, that's cool, okay. We'll just erase that because traditionally we just don't write the ones. And now we have to times it by the other piece. Some other action on our inversion boundaries of this hyperbolic system. The inversion boundaries of this hyperbolic system, okay? Cool. Which take place on Planck constants and so on. But when we solve this one, we get square root of the Gieseking constant times J1 minus J2 times our box. Okay, I skipped a couple steps here, so I'm going to try to fill them in. I thought I'll give you an example first. So on the right-hand side, what we get is there's some partition action using our roots, using the roots of our system. I could also rewrite copies of all these equations with minus signs, right? So plus or minus are both allowed. So here we have a J1 minus J2. And in this system, we were using the pluses. So let's write down the minus ones also. But I took half of it, not all of it, I took half of it. I took part of the roots to operate the transform with.
It's plus.
It's plus, thank you. Okay, and then this, so when we're searching, we have to search against all the combinations. It really makes it more complicated. We have to search all the partial combinations of this set of equations to land what geometry might explain under that root action, this exact number. Okay, and we get the square root of the Gieseking constant, which was new to a physicist. Gieseking constant, what's that? Okay, oh, it's the simplest manifold. There are more technical details and so on, but it's the more you look into it, the more you realize this is the most beautiful concept in manifold construction theory. It's at the base of how you get everything else. This is really cool, okay? But also it would make a lot of sense to have a bounded limitation, the speed of light, to have some sort of manifold boundary, because we know gravity does. We know gravity is bounded. At least Einstein was able to perfectly model gravity using a manifold, okay? If we also have a manifold, not just a manifold, but the smallest, simplest manifold there is, the limit of manifolds binding the limit of action, that would be a real great clue finally to start chasing about what's going on. Okay, so we get to do this with all the constants in nature now, follow the same process, and it takes a long time mostly because of this part. You don't know which roots belong to this constant. We don't know what part of the system it's using. We have to check them all for all of them. Okay, but it's not an infinite number. It's doable, totally doable. So that was the process. And from that process, you can come to the website, I'm sure you have already, and see the pattern, which is absolutely remarkable. In terms of Planck boundaries and operations that follow this coherence link, or this rule between two parts of the system, and this hyperbolic exchange connection rule, just those two rules alone, we can pattern all 280 of the constants in nature. These are things with many, many significant digits, and when they relate together, they relate constructively together too. The same sorts of boundaries all bind up in the pattern together, right? Not just by their actions and their boundaries and their internal actions. So there's a lot of patterning, as you can see if we scroll down through here. Even if you didn't know what any of the symbols meant, you could clearly see that there's a pattern going on, right? We've come to an algebraic connective structure that we can describe perfectly in terms of matrices, that we can then break up into its partial root transforms and connect those sets of partial root transforms to the actions of the constants in nature, landing within 5 sigma, in most cases right around 1 or less sigma, of the actual measurements that we're needing to land, the data points we're trying to make sense of. Okay, we're enthralled beyond where we could have been when we started looking for the pattern, because the constants that populate it, some of which I had never heard of before, connect together and talk to each other. You can use these two to make this one, and these two and this one squared to make that one. They're a closed, connected system of geometric parameters. Absolutely gorgeous. Not just the logic by which they're bound, but the geometric parameters that populate the logic are also logically bound. Okay? It's gorgeous and simple. Like pi and the Lemniscate constant are all the Lemniscate constants, right? You get the whole set. When you get a constant, a geometric parameter, you get all the ones that normally come in its family. The whole family just come together, and it's really nice.
What was the Lemniscate constant?
Pi, one way to talk about what pi represents is in terms of length or in terms of area, right? So if we have a unit circle, the length from here all the way to there has a one-dimensional value of pi. If we want to talk about the area of the unit circle, now the whole area has a two-dimensional value of pi. Two different ways to see it, they're both right. Just depends on how you want to be playing things. But pi interfaces with both of those geometric properties perfectly. Clue, which means it can transform between them. Okay, another one, so this is pi. We're all very happy with pi. It helps you see into the world more richly. Just the conversation of how one would come about measuring the value of pi gives you ideas about how to start seeing things and measuring things and looking into the world. It's a great Kickstarter into the coolness of geometry. This represents circles, though. It's tied to the geometry of circles. Okay, one of the reasons we like it so much, because circles are elementary, fundamental. The next most complex object you could make that still closes on itself and is cyclic would be either to go around twice before you connect, or if you want to stay the same number of times around, you go like this and go through the middle and oscillate like that into a lemniscate. Now we're still at 1 here and -1 there. All right, this one had an area of pi. It has a length of 2 pi. Right? So that's also a number in this circle. Any other numbers you can pull out of the unit circle?
I mean, you can go off dimensions.
Yeah, and you can also pull out relationships like between x and y, cosines and sines and all kinds of stuff like that, right? So there's a lot of content you can pull out of this unit circle, or circles in general. Now here we're going to ask the same sort of question. First of all, this was length and area and stuff information. What about here? What's the length?
S.
Yeah. Here, the whole way around, doesn't matter where you start, as long as you come back to the same point, is S. And the area of one lobe is 1. Exactly. The area is another 1, so the area is 2. The total area of the lemniscate is 2. See how it might be a useful object all of a sudden? At least algebraically, you can do a lot if you can use 2. Okay. Uh-oh, I have to go very, very soon. Give me 5 more minutes. Cool.
Where'd the S come from?
S stands for the arc length of this unit lemniscate.
Okay.
Unit lemniscate because it goes out to 1 and -1.
Now, are those 2 circles or
Those are,
figure eight?
it's like a twisted, it's like a figure 8. It's like a figure 8, yeah.
Okay.
Like a twisted circle. Okay. Clearly in this picture, quadrants matter because they're different. Right? This is different than this. If I turned it, you would recognize that something had happened. And this one, if I turned it, you wouldn't. Okay. So here we're going to ask what other natural numbers are we going to pull out? Well, here I could ask the same thing. There's people have already done it. We did 2 pi all the way around. We could do 3/4, 1/2. Right? We can do all the proportions, but the other one that's very common is to care about pi over 2 and all of its multiples. Okay? Because of the quartering of the system here. Here we quarter the system also, so we're going to do the exact same thing. We have S as a parameter of the system. We're going to take just one lobe length. And we're going to call it L, which is half of S. Okay, it's another feature. And then we're going to take 1/2 of it and call it L1. The first, this is the Lemniscate constant. This is the first Lemniscate constant. And then we're going to say pi over S equals L2 to get a second Lemniscate constant. S over 2 pi is Gauss's famous constant in geometry. And then we have the ubiquitous constant, which is Cu, and it equals the square root of 2 times the second Lemniscate constant. So these are all the Lemniscate constants and used in geometry, and all of them show up in our system. Okay? Really beautiful. I mean, centrally in our system, let me show you. Here. There we go. Here's a Lemniscate constant. In this picture right here, 1 over the Lemniscate constant using the same root transform as the speed of light uses. And we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 of them. Okay? 18 with one sign, 1 with another sign. If we go up a little bit higher, we run into the speed of light again, right here, which has a partner. Same string of digits, different dimensions. Interesting. Okay, so there's the story. We've come to a story, and the algebraic parameters, the geometric parameters holding the algebra together, fitting it together, are not just coherent, but they're the simple, beautiful ones that have been uncovered by Newton and everything that's followed in combinatorics. The Catalan constant, right? Everything connected to that story, the domino tiling constant. Yeah, there. That's where we're at. So we've posted all of these online, physicsmonastery.com. You just click on constants in nature and you go through each column. There's exactly 8 columns with 36 equations that represent 288 transforms, and they all follow this pattern, and they all act upon partial sets of the roots of this equation. Okay, they use part of it. They don't use the whole universe to do their action. They're using a specific part in each case. But each column is using the same parts. So they're grouped by the root transforms first. Then they're also grouped magically by their boundaries and the actions on the boundaries. So anyway, that's the pattern we've found. It's the first time we've ever found a rich connective pattern between the different constants in nature. So what we're trying to do is keep going, understand what it means, visualize it, code it, build our intuition off of the actions, and start making machines that can take advantage of that sort of connectivity. Okay.